Hey there, college algebra folks. I hope you're all doing all right and hanging in there. Um, I did want to give you a couple of quick examples over 4.3 and 4.4 work, just to make sure that we're all on the right page here in terms of what we are considering as we work through this material. What we do have going on in section 4.4, if we begin there, just to take note, is we are looking at the case of factoring polynomials, right? For example, here we have a nice polynomial expression. We're going to be interested in perhaps factoring that polynomial, breaking it down into what we think of as a product of linear factors and or irreducible quadratics. In that process of factoring, it is going to require us to do some division, right? In any factoring process, the process of division is going to be involved. So to begin with, what section 4.3 does is it delves into that division that happens with polynomials. It spends some time looking at and having you recall, and this is a bit of recall information. This is a topic that was presented back in 116. You're going to recall here what we call polynomial long division, and I'm going to also introduce you to the case for synthetic division. Now, if we look here, here is a polynomial long division problem. It is asking us to divide this quadratic statement from this polynomial statement, which does mean that we are going to perform a long division where we are going to divide x to the fourth plus 7x cubed minus 4x squared minus 2x plus 10. We're going to divide that by the quantity 2x squared plus 3x minus 8. Right? And in this division process, right, if you recall, it begins with these first terms, right? We can ignore pretty much everything else as we start off, and we just ask ourselves, what times this first term of 2x squared is going to give us this result of x to the fourth power, right? Well, we could note that in order to obtain the x to the fourth, I am going to have to take an x squared and multiply that by another quantity of x squared. X squared times x squared will yield x to the fourth. However, it will also, when multiplied by the 2, will bring along the quantity of 2. But we don't want that quantity of 2. We need to make that quantity into the quantity of 1, the coefficient that would exist here in front of x to the fourth. So to make the 2 become a 1 in this statement, we are also going to include the factor of 1/2. When we multiply the 2x squared by 1/2 x squared, that does produce the quantity 1 times x to the fourth power, or x to the fourth. Now, in the long division process, not only do we multiply this first quantity by that 1/2 x squared, we would continue to multiply the other terms of our divisor here also by that quantity. So 1/2 x squared times 3x is actually plus 3/2 x squared cubed, and the 1/2 x squared times the minus 8 will result into the quantity minus 4x squared. Where in the division process, we are going to subtract this entire quantity from these three terms given above. X to the fourth minus an x to the fourth is nothing in value, so that would leave behind a 0. Whereas 7x cubed minus 3/2 x cubed would be the quantity, if we go with common denominator, that would be 14/2 minus 3/2, that would result in positive 11/2 x cubed. Where when we now come along and take negative 4x squared and subtract a negative 4x squared, the minus the negative is like adding it. So this would be minus 4x squared plus 4x squared, and that result is 0x squareds. Right? Now we can drop down our other two terms, minus 2x plus 10, and repeat that process. right? Asking ourselves to begin with now, what times 2x squared gives me this first term down here, 11 halves x cubed. Now to get the x squared to turn into an x cubed, I am going to have to multiply just by a quantity of x. X times x squared will bring the x cubed about. But what do I have to multiply by the quantity 2 to make that into the statement 11 halves? And what I have to multiply by would be the quantity, that would be 11 fourths in value. If you take note, right, 11 fourths times 2, the 2 and the 4 would simplify into a 2 in the denominator, and that would leave us with 11 halves x cubed. So now 11 fourths x times 2x squared would be 11 halves x cubed. 11 fourths x times the 3x would produce plus 33 fourths x squared. And the 11 fourths x times the negative 8 would produce negative 88 fourths, or which we could simplify to negative 22x in value, where I am going to take that entire quantity and in the division process subtract it from these three terms above. Now, certainly 11 halves x cubed minus 11 halves x cubed is nothing, right? So that is our 0, and this is how the division process should be playing out, where we follow that with 0x squared minus 33 fourths x squared. Well, that will yield negative 33 fourths x squared. And negative 2x minus negative 22x is like negative 2x plus 22x. That would yield plus 20x. And we would drop down this plus 10 at the end. And we repeat the process, folks. We ask ourselves, what times this 2x squared is going to yield this negative 33 fourths x squared? And first of all, we'll note x squared is already part here, right? X squared and x squared, we're not going to have to multiply by any value of x. All we have to do is figure out what do we have to multiply 2 by to make it turn into negative 33 fourths. Right? So if we think about that for a moment, what would we have to multiply 2 by to produce negative 33 fourths? And if you're struggling with that, now notice we might go off to the side and set up a little side problem here. We're kind of asking ourselves, 2 times what number x equals negative 33 fourths? And how would we solve that for x? Well, to solve that for x, we would divide both sides by 2, which is the same as multiplying both sides by 1/2 in value. So if I multiply the left and the right by 1/2, I will find that what we need is x equal to negative 33 eighths. So negative 33 eighths is what I have to multiply this 2 by in order to produce negative 33 fourths. All right? Negative 33 eighths times 2 would yield, times 2x squared would yield negative 33 fourths x squared. And negative 33 eighths times the positive 3x would yield negative 99 eighths x. And the negative 33 eighths times the negative 8 would yield plus 33. And what I want to do here is subtract this quantity from above. Right? Take this entire quantity here again in this division process and subtract it from what we have above. Certainly negative 33 fourths x squared minus negative 33 fourths x squared yields nothing, a 0 there. Whereas 20x plus, well, minus negative 99/8x is like 20x plus 99/8x. And if we go common denominator, this would actually be 160 eighths plus 99/8 is going to yield positive 259/8. Right? X. And then here at the end, we would have 10 minus 33, which would be negative 23 in value. Now, folks, at this point, we're going to be looking at this and going, all right, what times 2x squared gives us this? And the answer is there isn't a value. What we've obtained down here, this quantity that remains, since its power of x is less than the power of the divisor, since its degree is less than the degree of the divisor here, we have reached what we call our remainder in this case. Right? And how we've handled remainders in our division process is we will always add that to what would be our quotient by placing it in a fractional form over our divisor. This would be our quotient. This would be our remainder over our divisor being added to that quotient. Hey there, college algebra folks, back with another quick example here. Again, we are looking at using the division process to help us factor out a quantity from a polynomial value, right? Factor out, in this particular case, we want to divide this linear factor x plus 6 from this polynomial factor given by x to the 5th minus 2x cubed plus 6x minus 1. And it asks us to use this process that is new to us, that's going to be known as synthetic division. And what we're going to see as synthetic division is a way of simplifying the case for polynomial long division. In fact, if I was to go through this through just another case of a long division for you, take note that in the long division process, and even in the synthetic division process, one thing we are going to want to keep track of is any zero terms. We are missing a few terms here. This is x to the 5th plus 0x to the 4th minus 2x cubed plus 0x squared plus 6x minus 1. And what we want to divide from that is this quantity, x plus 6. All right? And as we've seen in the division process, we do start by asking ourselves, what times x gives me x to the 5th? And that quantity is actually just x to the 4th in value. X to the 4th times an x is x to the 5th, whereas x to the 4th times the 6 is plus 6x to the 4th. Where we are going to subtract that from what's above. If we subtract that from what's above, this will yield 0 minus 6x to the 4th. That minus, don't forget to distribute. Bring down the rest, minus 2x cubed plus 0x squared plus 6x minus 1. And I start the process over. What times x gives me negative 6x to the 4th? And that would be minus 6x cubed. Minus 6x cubed times x gives me minus 6x to the 4th, and minus 6x cubed times positive 6x is a minus 36x cubed, where I'm going to now come along again and subtract that from what's above. Negative 6x to the 4th minus negative 6x to the 4th is plus it. And that leads us to 0 again. And then we have minus 2x cubed minus negative 36x cubed is actually negative 2x cubed plus 36x cubed, which would be plus 34x cubed. Bring down what's above. and start the process over. What times x gives us 34x cubed? Well, that would be plus 34x squared. Now you can see this polynomial long division is what we're doing here. This is not synthetic division yet. It is a rather long and tedious process, and there's a lot of opportunity for mistake in here. And I think we've been all right so far, where we now start by saying, okay, yeah, 34x squared times x is 34x cubed, and 34x squared times 6, now that would be 30 times 6 is 180. 4 times 6 is 24, so 180 plus 24 is 204. So this is plus 204x squared plus 6x minus 1. And we subtract, I should be careful there. We're not bringing that down quite yet. We're going to just subtract this quantity from above, and these are going to be dropped down to 6x minus 1 down here. All right? We do end up with 0. And then 0 minus 204 is negative 204x squared. And we say, okay, what times x gives us negative 204x squared? And that would be minus 204. If we go negative 204 times x, that's careful there, negative 204x. That produces negative 204x squared. Negative 204 times 6. Now, 200 times 6 is 1200. 6 times 4 is 24, so this is actually going to be minus 1224 x's, right? And we're going to subtract that from above and bring down the minus 1. Negative 204x squared minus negative 204x squared is 0. 6x minus negative 124x, or minus 1,224x, is 6x plus that quantity. So this would actually be 1,230x. Right? Now, what times x gives us 1,230x? Well, that would be plus 1,230. 1,230 times x is 1,230x, and then 1,230 times 6. Now that I will go ahead and break out a calculator for. 1,230 times 6 is 7,380. So this would be plus 7,380. We're going to finally subtract that from above. This gives us 0, and then this would be minus 1 minus 7,380. So that would be 7,381 negative in value. So what we note then is the degree of what we have here is now less than the degree of our divisor. So this must be our remainder. This is our remainder in the division. Right? This quantity up here, this is what we call our quotient in the division. All right? That is, again, polynomial long division, and it is a rather long, tedious process, or at least it can be. What we want to look at now is making our life a little easier here by performing some synthetic division. What we're going to see that when we get into the polynomial, the process of factoring a polynomial, oftentimes our polynomials are going to take on a linear form. This linear form, I think we've discussed it in class before we left on break. That was in the form x minus r. Right? Well, that's going to happen quite often, and we're going to be dividing out these forms x minus r quite frequently from polynomial statements. So there is a case where when we do divide in this manner, right, all that division can be simplified using a process known as synthetic division. Right? In the synthetic division problem, right? If we were to set this back up again, the polynomial division would look like this. As we had noted, we would have to make sure we include any of our missing terms with coefficients of 0, and we see that I've done that here, right? And we would divide out this quantity x plus 6. Whereas if I'm going to approach this using synthetic division, this is the case for polynomial long division, right? What we're going to set up now is the case for what we call synthetic division, right? In this scenario, how synthetic division develops is as follows. You're going to have what represents your divisor. Oh, sorry, this would be your dividend. Your dividend underneath the division symbol, and out here would be what would represent your divisor. Now, what would be our dividend in this case? We're just going to bring down, from the case for polynomial division, the coefficients, right? The coefficient of 1, 0, -2, 0, 6, and -1 from these, what we would say, 6 terms given here in the dividend of our division problem, right? The 1, the 0, the -2, the 0, the 6, and the -1. And we kind of want to space them out. We want to make sure that these are representing different values down there, right? We don't want to confuse the two and mix them up, right? Now on the outside in the setup for synthetic division, we're going to have what's going to represent our divisor. And if our divisor's in the linear form x plus 6, we're going to use what we see here as the opposite of what we're adding to x, right? We're going to actually use what we know as the 0 for this factor. This factor, x plus 6, has a 0 value of -6. So we're going to use -6 out here to represent the value known as our divisor. And here's how synthetic division works, right? Nothing is produced up here. We're not going to have anything happen above the division bar. First of all of it's going to happen down below the division bar here. Excuse me. What's going to occur down below is going to start off, right, by simply adding 0 to this very first coefficient, to the leading coefficient. If we add 0 to 1, right, that's going to produce the result of 1. We're to continue here. I'm now going to take the -6. I'm going to multiply it by this quantity of 1. And I'm going to put that product right here underneath the next coefficient of 0. So -6 times 1 is -6. That -6 is going to go right here as an answer, -6. Where I repeat the process. I take 0 plus -6, that's -6. I then take -6 times -6, that is positive 36. -2 plus 36 is 34. And -6 times 34, well, we've done that math already. These numbers should start to look familiar. That is the quantity what? -204. Right? That should look familiar. Where if I add 0 to -204, that's -204. Now I do want to keep these separated, right? Where -6 times -204, we've done that math before also, right? That is what? That ends up yielding, I think we found it to be 1,200 and, well, no, let's be careful there. Let's just go through it. Because it is 204 times, oh yeah, well, yeah, we did this one. That is 1,224. I just wanted to make sure we had that right. So that would be positive 1,224. Yes, now when we add vertically, we should see that familiar value of 1,230. Negative 6 times 1,230, that gave us our final result here, which was, careful here. Well, yes, the result negative 7,380. Where when we added vertically here, we ended up with this familiar number, negative 7,381. All right. Now, how are these numbers familiar to us, right? If we note these first 5 numbers given here, right? Those were, if we look back, let me fold this example over here so we can kind of see. These first 5 numbers here, 1, negative 6, 34, negative 204, and 1,230, these were the coefficients seen in the terms of our quotient. The divisor up here started at an x to the 5th power. The quotient is going to begin at a quantity of x to the 4th power. Minus 6x, and then we just continue on here, reducing by powers of 2, plus 34x squared, and so forth. This does produce the answer x to the 4th minus 6x cubed plus 34x squared minus 204x plus 1,230. This does become our new quotient, right? Or the quotient that we had found using this polynomial long division. Whereas, what's this number? Right? If you look back at the polynomial long division, that number, if I bring this up here, that number was our remainder up here, right? Negative 7,381 was the remainder that we had when we performed this polynomial long division, right? This is going to become our remainder. All right? This is going to form our, what? We've set it the coefficients of the quotient in our problem. Right? If our divisor starts at a power of 5, our quotient would start at 1 degree less than that, at an x to the 4th power in this case. All right? That is the process of synthetic division, and you can notice it fits all right here. And it involves a rather very algorithmic process, where all we did was start by adding 0 to 1 and giving 1. Take negative 6 times 1 is negative 6. 0 plus negative 6 is negative 6. Negative 6 times negative 6 is 36. And that algorithmic process just continues on down the line until at the very end, this last number is going to be a remainder, and these previous values were going to be the coefficients of your quotient. Right? So folks, that is just again another quick example over polynomial long division, but really what I want you to spend your time focused on is learning this synthetic division process. Right? Synthetic division makes polynomial division extremely quick. If we go back and I give you another just real quick example. Let's say we had the polynomial long division x to the 4th minus 7x cubed plus 6x squared plus 2x minus 3. And let's say we were going to divide that by x minus 2. All right? Now that polynomial long division could take quite a while, whereas in synthetic division, I would just drop down these coefficients from the dividend, right, including any 0 coefficients. Now I don't have any 0 ones, so it would just be those numbers there. On the outside, I would take what would be the 0 of the divisor. Now the 0 of the divisor is the number 2. Plug in 2 there. 2 minus 2 is 0. So the divisor would be, the 0 of the divisor would be 2, and the process just starts by adding 0. 1 plus 0 is 1. 2 times 1 is 2. Negative 7 plus 2 is negative 5. 2 times negative 5 is negative 10. 6 minus 10 is negative 4. 2 times negative 4 is minus 8. 2 minus 8 is negative 6. 2 times negative 6 is negative 12. Negative 3 plus negative 12, negative 15. Right? This is our remainder. These are the coefficients of our quotient. This started at an x power of, what, to the fourth power. So this is going to start at one less than that, x cubed. So if we go back and think about what would have been our quotient up here, it would have just been x cubed minus 5x squared minus 4x minus 6, where we would have a remainder of negative 15. All right, folks? So that is synthetic division. It's a division process that we can use when our divisor takes on this format x minus c. It only works in this case, folks. In this process, then, this number we use here is going to be our value of c. These are going to be the coefficients. Hey there, college algebra folks. Got another quick problem for you here from section 4.3 and 4.4 material, where what we are dealing with is a polynomial function we can see, and we are told a couple of zeros regarding that polynomial function. And it does give us a little hint here to determine the factored form of f of x using what we call the factor theorem and polynomial division. All right. Now, where we begin is by noting that if these are two of our zeros for this polynomial function, that this polynomial function is going to have a couple of factors that give us these as zeros, give us these values as zeros. What are those factors? If we start to think about f of x, the first factor with respect to x minus 5 is going to be the factor x plus 5. And the second factor with respect to the 0 of x minus 4 would be the factor x plus 4. Where when we think about this polynomial function, then, there does remain this portion here, all right, which we have to still determine. And the value here of the unknown portion of this factored form can be found using a little bit of polynomial division. The factor theorem is what allows us to make this conclusion about our factors. Polynomial division is what we're going to use to find this remaining factor. And if you remember from our cases for division, there's a couple of ways we could do this division. We could do a long division involving x to the fourth plus 12x cubed plus 37x squared minus 30x minus 200, and we could divide that beginning with our first factor of maybe x plus 5 and continuing from there. Or what we might actually consider doing is a little synthetic division here. Right? If we set up the synthetic division, bringing down the coefficients from our polynomial, that would be 1, 12, 37, negative 30, and negative 200. And our divisor would be given by the 0 that corresponds to this factor. Now, we are told that 0 was negative 5 back here. So we're going to use the negative 5. And remember, in the synthetic division problem, this all starts by adding 0. 1 plus 0 is 1. Negative 5 times 1 is negative 5. 12 times negative 5 is 7. Oh, sorry. 12 plus negative 5 is 7. Negative 5 times 7 is negative 35. 37 minus 35, right, is 2. Negative 5 times 2 is negative 10. Add. Negative 40. And negative 5 times negative 40 is positive 200. Add. We get 0. Now keep in mind, this is our remainder. And this would be, out here, represents what we would call the coefficients of our our quotient here for dividing this quantity by x plus 5. Now, I will tell you that tells us this remaining portion up here, if we think about the x plus 4 and this unknown quantity, that would actually be x cubed plus 7x squared plus 2x minus 40, where we would see that the x plus 5 would divide out evenly. That's why we have a remainder of 0, and these values here would become the coefficients of this reduced factor, what we sometimes call a depressed equation or expression. But what I'm going to want to do with this quantity x cubed plus 7x squared plus 2x minus 40 now is factor out the x plus 4 from it. And the way I'm going to do that is by dividing it out. And I could carry out that division again using, again, a little bit more synthetic division. And this is what's nice about synthetic division, folks, is to carry out a second round of it, I can carry that out right below here with the result from my first case for synthetic division. Involving this 0 of negative 4, right, from the factor x plus 4, I would bring that negative 4 out in front. All right, and start the synthetic division process again. I would add 0 to 1, that gives me 1. 1 times negative 4 is negative 4. Add vertically, 7 plus negative 4 is 3, right? Negative 4 times 3 is negative 12. 2 plus negative 12, or 2 minus 12, is negative 10. Negative 4 times negative 10 is positive 40, and when we add vertically here in this last column, we get the result of 0. Now again, this is going to be our remainder, and what we do see is because we have a remainder is 0, x plus 4 must divide out from this depressed expression evenly, and it does. What it leaves behind is this statement here, this quantity. If we think about this unknown, this question mark that we had in our factored form, its coefficients are going to start with 1, 3, and negative 10, and the degree is going to be 1 less than the third degree, which is going to start at the second degree. So starting here, this is going to be 1 times x squared. That would be x squared plus the 3 times an x minus the quantity of 10. So there is the beginnings of our factored form. To finish now, what we do want to note is, can this quantity be factored any further? At this point, we've obtained a quadratic, and we can rely on quadratic methods to finish our factoring. Now, if we take a quick note here, we can note that this does factor into two factors, where the first factor would be plus 5, and the second factor would be minus 2. What we would notice is 5x minus 2x does give us positive 3x, but 5 times negative 2 is minus 10 in value. So in the end, right, if we gave a final answer here, and we think about the factored form of f of x, it is going to involve this factor x plus 5, but take note, this factor happens twice. So we would say that would be x plus 5 squared, times this factor of x plus 4, which we were given initially with the information about this 0, times this last factor of x minus 2 that we obtain when we factor the final quadratic here, x squared plus 3x minus 10. This becomes the factored form of that polynomial. And we used the zeros to help us find that, along with the factor theorem to break out these two factors. And we used a little polynomial division here, folks, to actually perform the factoring, to figure out how the, what we might say are these depressed equations or expressions came about when we divided out these factors. Hey there, college algebra. Back with another quick example here from sections 4.3 and 4.4, specifically 4.4. 4.4 focuses on the factoring of polynomials. Again, 4.3 is the polynomial division. So we're going to use a little of all that here in this problem. If you notice here, again, it says, suppose we have this polynomial function, and we're asked to determine the factored form of f of x using what we call the rational zeros theorem, the remainder theorem, the factor theorem, and what we know as polynomial division here, folks. All right? And the way we go about doing this, folks, is we do start with what is known as the rational zeros theorem, which tells us if we want to make a list of potential zeros, right, our focus is going to be on the coefficient in the very first term and the constant value at the end, right? If we call the constant values factors at the end the value of p, and if we think about values of p being the factors of negative 18, right? Well, those factors are going to be given by plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, plus or minus 9, and plus or minus 18. Those are going to be our factors of negative 18. All right. The potential zeros theorem is also going to have us look at the factors of our leading terms coefficient, that being the factors of q here, right? If we call q the factors of, now notice in this case we have a rather simple leading coefficient there, and that is the value of 1. Those factors are simply plus or minus 1. All right? Our list of potential zeros then is going to be given by every single combination of value we know as a value of p over these values that we call out as the value of little q. Right? Our list of potential zeros, we might say, are going to be our p over our q values. And if we take note, putting these numbers of p over just the value of 1, plus or minus, is just going to return these values we know as p. So in terms of our list of potential zeros, we could just restate. It is just going to be a restatement of what is our value of p here, since the only little q value we're considering here for the coefficients of 1 is just the value of 1. So here are a list of potential zeros, folks. These are possibilities, right? We know that if we were to factor this value in negative 18 at the end would come from all of the products of the constant terms in all of our factors. So we're going to go back and look at the what would be constant terms in all of our factors, which would be given by the factors of negative 18 here. Whereas we would also then have to involve the factors of our leading term, right? When we go from that factored form to that polynomial form, we know this leading term is going to come from all the factors of our leading term. So we look at all the factors of our possible leading terms, and those are all going to be plus or minus 1 here. All right. Now that is the beginning. That is using what we call the rational zeros theorem. And one thing we want to point out here is it only gives us the rational ones. This isn't going to point to any irrational zeros. This isn't going to show us any of the zeros, like maybe the square root of 2 or maybe the value given by pi, right? We're not going to see irrational values that cannot be written as a ratio appearing here. But we might run into rational values, like we've seen here, these nice integer values, right? Whole number values, plus or minus. Along with, we may also encounter at times really any real number other than those irrational. So you could think of 1/3. 1/3 would be on here. 3/2 could come out as a possibility. It just depends upon what are your different factors of p and q. All right, so that's the rational zeros theorem. What we're going to now do with these potentials is test them, right? We're going to test them using what we call the remainder theorem to see if they actually are a real zero. One of the ways the way that we're going to go about doing this is we are just going to plug them into our function f of x. Right? We are just going to substitute in these different values into our function f of x, and we're going to be looking for the cases when f of x would turn into 0. Now, folks, this can be a little bulky, right, to calculate for each and every one of these values. Keep in mind, you do have your calculator, right? You might consider going into your calculator here, going into your y equals menu, and actually putting in your function. So we would put in, for instance, x cubed, right, plus 8x squared plus 9x minus 18. Now, let me just double check that that is right. Plus 8x squared plus 9x minus 18. And now consider going over to my table settings, making sure my independent variable is turned to ask, and then jumping over to my table. Second graph will bring up your table. Second window will bring up your table settings. And there I can make my table of values. For instance, I can plug in 1. Oh, and right away we see that the value of 1 produces a value of f of x equal to 0. What does that tell me is that the factor x minus 1 must divide my function evenly. Because if I plug in 1 and my function equals 0, I know that I have a 0 of that function there, folks. So what does this tell me is this does tell me that I have the factor, this leads me to the factor x minus 1. And what I could start to do here is to factor that from my polynomial. And the way that we factor that from our polynomial, right, is we could use a little synthetic division. Again, this is why synthetic division is so nice, folks. It's a quick process, right? It's a quick algorithmic process that doesn't take up a ton of space either, right? Right here, we can note the dividend value would be made up of the coefficients of our polynomial. The divisor value would be made up of the 0 that we just determined, right? And the process begins by adding 0 to our first coefficient in the dividend, taking then our 0 times that result and placing it under the next coefficient. So 1 times 1 is 1, and add. You get 9. 1 times 9 is 9. Add, you get 18. 1 times 18 is 18. Add, and you get 0. And again, this is confirming that we are on the right course, right? We do see we get this value, this result of 0. Right? So that starts to tell us that if we think about our polynomial up here, f of x can first start to be factored as x minus 1 now, times this remaining portion. That would be x squared. Well, what am I doing here? I'm looking at the screen versus looking at my paper. X squared plus 9x plus 18. Now that is a nice form. We started with a degree of 3, so here we have a quadratic. We can now rely on other methods to factor this quadratic. We might consider here then, all right, does that factor any further? Well, certainly let's see x and x, two numbers that multiply together to give us 18, that we can add or subtract in combination to yield 9. And what can we see there, folks? That would be plus 3 and plus 6 will work. All right, so f of x in its factored form would simply be x minus 1 times x plus 3 times x plus 6. That would be the factored form of our polynomial function here. Notice I only had to test 1, 0 to find this here. Now, I could have started with any of these numbers, and actually if you look back, you will see that this is a case where x would be a -3 as a 0, and this would be the case for where x would be -6 as a 0. And if we actually go back to our calculator and double check that, we would see that certainly -3 gives us the value of 0, and so does -6. Whereas if I tried to test any other number in there, right, they do not indicate values of zeros, so they are not what we call zero values. They are not going to give us what we think of as a remainder of 0, right? This is all the zero theorem in action. Whereas the factor theorem is what allows us to go back and say, all right, this is 0, So that means these must be factors of x plus 3 and x plus 6. And it's this polynomial division that allows me to divide out these factors from my polynomial. All right, so that was another quick example over factoring polynomial. Their college algebra. I got one more quick example for you here on factoring polynomials. Here we see that we have a fourth degree polynomial, and again we're asked to determine the factored form of f of x using the rational zeros theorem, the remainder theorem, the factor theorem, and polynomial division here. If you watched the other part, you probably have worked through one of these already, but we are going to make our list of potential zeros. All right. Remember, these are going to be given by p over q values, where if you think about your p values, those are your factors of negative 24. If we think about the different numbers that multiply together to give you 24 in value, or negative 24, that would be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 8, plus or minus 12, and finally plus or minus 24. If we think about the values that give us q being the factors of our leading term, right, it's coefficient, those would be the factors of 2. Those are the values plus or minus 1 and plus or minus 2 in value, right? Those would be our factors of q. So in terms of our potential zeros, p's over q's, right? So our p over q values, our potentials, are every single possible combination of a p value over these two different values for q. If we go through that and we put, first of all of these p values over 1, that is just going to repeat our p values. So that would be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 8, plus or minus 12, and plus or minus 24. Where if I now come back and put all my p values over a q value of 2, I have a few more that are going to appear, and one thing we want to keep in mind is we don't want to repeat any of these, right? So for instance, 1 over 2 is 1/2. So 1/2 is not repeated, so plus or minus 1/2 is also a potential rational zero. All right? 2 over 2, though, is 1. We've already used 1, so we're not going to repeat it. 3 over 2, though, is 3/2. We haven't used 3/2 yet, so 3/2 is a potential. 4 over 2 is 2, we already have it. 8 over 2 is 4, we already have that. 12 over 2 is 6, that's already on our list, and 24 over 2 is 12, and that's also already on our list. So we don't have too many fractional potentials, but we do have these cases for 1/2 and 3/2. Right? That's a rather long list. All right? Remember, to test our zeros, we are going to consider making a bit of a table here, right? Not a table for all of these, but we're going to begin testing these, perhaps at the lower end, of numbers, and see what we have turn out here. I will go back and remember a good way to do this is on your calculator, right? So if we clear out our last example, this is 2x to the 4th plus 4x cubed plus 2x squared plus 16x minus 24. We double check. Plus 2x squared plus 16x minus 24. And now if we go over to our table, we can actually see a few already appear. Let me go ahead and just delete this out and start fresh. I believe saw maybe that first 0 of 1 also appear. So yeah, if we begin here, 1 is our first 0. That does mean we have a factor of x minus 1, right, in our factored form. If we apply a little synthetic division to factor that out, we place the 0 on the outside, and we bring our coefficients into this the dividend of this synthetic division here. The This is 2, 4, 2, 16, and negative 24. Start the synthetic division process by adding 0 first. 2 plus 0 is 2. 1 times 2 is 2. 4 plus 2 is 6. 1 times 6 is 6. 2 plus 6 is 8. 1 times 8 is 8. And 16 plus 8 is 24, where 1 times 24 is 24. Negative 24 times 20, or plus 24 is 0. There's our remainder. All right. Here's the coefficients of our depressed expression. This started at an x to the fourth. This is for an x cubed, starting at an x cubed. We will notice that's not quite quadratic yet. So we do have to test a few more numbers in our list. If we test a couple other values then, right, we might test -1. Notice -1 is not a 0. If we test 2, 2 is not a 0. If we test -2, -2 is not a 0. If we test 3, 3 is not a 0. If we test -3, -3 is a 0. Right? So that does say here that -3 is a value of x that makes f of x equal 0, which does imply that x plus 3 is now also a factor. And we can factor that from the depressed format for the cubed case, the cubed depressed expression here, starting by adding 0 and multiplying, right? -3 times 2 is -6. Add, you get 0. -3 times 0 is 0. Add, you get 8. And -3 times 8 is -24. Add, you get 0. Right? Here is your depressed expression. This was an x cubed. This is going to be an x squared. And what we might note at this point, right? F of x looks like this. It is this factor, x minus 1, times this factor, x plus 3, times this depressed form, which is 2x squared plus 8. Now from that, we could factor out a 2. Maybe say this is 2 times x minus 1 times x plus 3 times the quantity x squared plus 4. Where if we spend a moment looking at this quadratic and considering its factor, we might notice it's how it would factor. We might notice it's an irreducible quadratic factor. All right? This is an irreducible quadratic factor. All right? So it doesn't factor in the real number system. If we were to consider factoring it in the complex number system, what we would take note is that x squared plus 4 equals 0, right? When what's true? Well, that's when x squared equals -4, or when x equals plus or minus 2 times I. So what our factors would actually look like if we were to factor this in the complex form, we might say here in the complex number system, right, f of x would actually look like 2 times x minus 1 times x plus 3 times the x squared plus 4 factoring into x minus 2i times x plus 2i in value. Right? Most of our work is going to happen in the real number system, so stopping here would be just fine. But if you did go on and look at some of that My Math Lab work, the My Math Lab work may be looking for at times the complex factors, or at times it may also be looking for what are called your complex zeros, folks. All right. So take note here. All right. Let's see if I can just bring that all up so you can see that a little clearer. If that's right, a little glary there, but this is what we see going on in this case. All right. I hope that helps everyone, and I'll have another round of examples here, looking at section 4.5 material, folks.